done. It's not quite been 30 minutes, but close enough. So I'll start in the new segment now. We're actually going to do the problems.
Parts.
Yeah, breaking it into reasonable parts. Trying to be sophisticated here. Okay. I also wrote down some formulas. You may be wondering, like, what formulas do you really need to make sure you know? So let me just make a list of a few formulas. So these are handy formulas. I may not even mention all of them, but let me just mention a few of them here. These are like formulas that, you just have to know them or you're not going to be able to do the problems. So you really do need to, if you need to make flashcards, just make flashcards, right? One of them is the integrating factor formula, the capital I of x, right? If you don't know this formula, you can't do the linear differential equations. So this is e to the integral of p of x dx, and that, of course, is with the understanding that you are solving a linear equation of this nature. Y prime plus p of xy equals q of x. So your differential equation has to be in this form, first of all. It's not always given to you in this form, right? You sometimes have to do some algebra first to get it into this form. But the p of x right here is the exponent of that integration, of that exponential function inside that integral. Okay? So that's an example of a formula that you need to know. A second example would be the change of variables that you have to use. So u is equal to y to the 1 minus n. This is for Bernoulli equations. For Bernoulli. Let me just remind you the Bernoulli equation as well. The Bernoulli equation is one that says u prime plus 1 minus n u, I'm sorry, p of x times u, equals 1 minus n times q of x. This is what the Bernoulli equation transfers into after you apply this change of variables. So you don't really need to know the whole process of how the change of variables actually works mathematically. Just in terms of nuts and bolts of solving these problems, what are the things you need to know? Well, first, you do need to know what does a Bernoulli equation look like, right? The Bernoulli equation is basically, here, I'll write it down right here. It's basically just like this linear one over here, except that on the right-hand side you have some power of y, which I always call y to the n, right? You need to know that that's a Bernoulli equation and that to convert it to a linear one, you need this change of variables and this is what it becomes. Okay? So there's a little bit of memorizing that you have to do for that, but all in all, it's not too bad. Does that look familiar to everybody? Can I remember that? Hopefully you all studied this for the quiz that we took a couple of weeks ago, so that might have been something you've already gone through once. Then we have the same kind of thing for the homogeneous differential equations. So everybody remember the homogeneous ones? On the homogeneous differential equations, you have basically y prime equals f of x and y. So you can put it into this form here, where the y prime is by itself. And the expression that's on the other side of the equation has to be such that if you attach t's to every single x and every single y, they basically can be crossed off. They basically cancel out. Okay, so if you have a homogeneous equation, then hopefully you guys remember that what we can do is I used v for this one, we can write v as y over x, okay? So this is the change of variables for a homogeneous equation. Or in other words, y is equal to xv if we rearrange it, okay? And that, of course, implies that y prime, by the product rule, is xv prime plus v. So you need to substitute these two formulas into the equation so that you get rid of all of the y's and y primes and have everything expressed in terms of x and v. Make sense?
My terms is just separate.
This always becomes separable, exactly. Bernoulli equations always become linear, and homogeneous equations always become separable. No exceptions to that. Okay? Yeah, go ahead, Doug.
If you have like x squared, that becomes t squared, correct?
Right, when you attach the t's, every time, so if you have multiple x's, then you get multiple t's with that match it. The t's are like measuring the weight of the term. So every x and every y has a weight of 1, and those t's are just keeping track of that weight as you go along. Okay, what else do I have on my list here? I have Newton's law of cooling. Okay, so there's a differential equation for that. This has to do with the rate of change of the temperature as a function of time. And if you remember, it's negatively proportional to the temperature difference between the object and the medium. So you take T minus Tm, you put a constant in front of it, and that constant, well, it typically had to be negative, so we put in the minus sign so that the constant was positive. So this is always with K greater than 0 in that context. Okay? This is the actual differential equation. Now, everybody should also be able to solve that differential equation. Okay? You might even remember the solution. I'm not putting that down as something to memorize, because I don't like to memorize things that I should already be able to derive anyway. I should be able to derive the solutions of this, because this is separable, right? You can get all of the capital T's on one side and all of the little t's on the other side, integrate both sides, and solve for the big T. You have to do a little bit of exponentiating and renaming constants as you go along. So it's a few steps, but you get the solution. I'll write down the solution just so you know what I'm talking about, but this is not the, I'm not going to put this one in a box. This is not the one that you need to memorize. Temperature of the medium plus a constant times e to the negative kt. I think we got to C2 by the time we had done the algebra on that. So it basically looks like that. Okay? So, but make sure you know how to derive that one, not just have it memorized. Yeah, Curtis.
So when we go to solve Newton's law of cooling problem on the test, if we don't write out the deriving and we just go like...
If you go straight to here?
Yeah.
If you go straight to here and then solve it out, you'll be totally fine.
Okay.
That would require you to have it memorized, but more than likely, I will tell you right now, I'm more than likely to ask you to derive this formula.
Oh, okay. All right.
If I ask you to derive it, and so derive the solution to Newton's law of cooling, part A. Part B is, all right, now solve this Sherlock Holmes mystery or whatever.
I see.
Some of those problems that we saw. Right, so, because if I only ask you to solve the Sherlock Holmes problem, which starts from here, you really aren't doing any calculus, right? You're just doing high school algebra to solve this equation. You just need basic knowledge of exponential and logarithm functions. These problems, by the way, are often riddled with exponential and logarithm expressions that you probably won't know off the top of your head. So if you have to give an answer that's in terms of the natural log of something or e to some power or something like that, that is completely fine. Okay? No need to simplify stuff too much. You were taught over and over and over again in high school, simplify your work, and I'm here to tell you, you don't have to do that. Okay? You can leave the numbers unsimplified. It's totally fine. Because we all have calculators and we can all go home and do the actual calculations. That's not as important to me as just knowing that you know what the concept is, what the topic is about, and how to solve it. So, the method, basically. Okay, let's see. Then there is number 5, I guess, is the mixing differential equation. This one for the rate of change of the amount of a chemical. So we denoted that with dAdt, and then it was plus R2A over V, but the V is the volume, and that's just the initial volume, which is V naught, plus R1 minus R2 times T. I probably, in the notes, I probably just wrote this whole denominator as just capital V, right? But the formula for capital V is V naught plus R1 minus R2T. And then on the other side, we have R1C1. So this is the equation. Remember, R1 and C1 are the rate in and the concentration in. And the R2 is the rate out. And the V is the volume, right? And your goal would be to solve for capital A of T. Okay? So this is linear. This is always a linear equation, and it's a word problem. You would be given all of the numbers that you need to solve that thing out, right? So you'd know what, you'd be given R1 and C1 and R2, and you'd have to just trust me that I'm going to make the numbers simple for you. They're not going to be complex numbers. Okay? All right, so that's that. Okay, there really aren't that many more formulas. Let's write down just a couple more. A couple more formulas. I'm up to number 6, right?
It's number 5.
No, wait, that
Oh,
was
yeah,
number
well,
5.
this-
Oh, on my handout, right? Yeah, I'm doing them in a little differently here. Number 6, the formula for the inverse of a 2x2 matrix. Okay, so if I take the matrix A, B, C, D, and I want to invert that, right? Everybody should just know this formula cold because it'll save you countless effort. For example, so imagine that you're trying to come up with a counterexample to some statement that I tell you is false. Right? Maybe I do something like this. Here is a false statement. I'm just making this up right now. I know this is false, but I probably haven't shown it to you before. That's not true. And suppose I tell you that's a false statement. Give me an example. Wouldn't it be nice to know the formula for the inverse of a 2x2 so that when you're explaining your example and checking it, you don't have to work so hard. You don't have to do a Gauss-Jordan reduction to all 3 of these matrices to get the inverse, right? That would take forever. So you really wouldn't want to do that. So this is just nice to know. 1 over AD minus BC. We swap these numbers and we put negatives on the other 2 numbers. Let's go with something like that. That look good so far? Okay, and then more generally, I'll put number 7 down as related to number 6, which is that just in general, if you want the inverse of a matrix, a good way to think of it is it's the 1 over the determinant of the matrix times the adjoint of the matrix. Okay, which is exactly what this formula is a special case of. See, the determinant of the 2x2 is just AD minus BC on the bottom. And this matrix right here is just the adjoint of the original matrix ABCD. Remember the adjoint? That's the next formula. The adjoint of capital A is just the transpose of the matrix of cofactors. It's just the transpose of the matrix of cofactors. So let's just do a real quick example. If I take ABCD and I want to know the 1,1 cofactor of this matrix, remember how you get it. You cross off the first row and column. That leaves you only D, right? So the determinant of just D is D. And that becomes the 1,1 cofactor. And of course, when you transpose the 1,1 position, it doesn't move because it's on the main diagonal of the matrix. So the D is just going to end up right there. On the other hand, what about the 1,2 cofactor? If I go back to the original matrix, what is the 1,2 cofactor of this matrix?
Negative
1,2 cofactor. I did not say the 1,2 minor. I said the 1,2 cofactor. So 1,2 cofactor, I cross off that row and column. This is what I get, right? But I have to take a negative of that, right? So the 1,2 cofactor is negative C. So when I do the adjoint, I'm going to transpose that from the 1,2 position down to the 2,1 position, and that's why I get negative C right here.
Would that be positive? That is plus minus plus minus, or minus plus minus.
It looks like this, right?
Oh yeah, it's pattern. Oh yeah, draw it out. Yeah.
Yeah, always start with plus in the left corner, and then just alternate as you go across rows and down columns. Yeah. Okay? So actually, this is a nice little, this is an oversimplified example. I expect you guys to be able to do bigger examples than this. But at least for this 2x2, you can find these 4 cofactors. They are just basically the same four numbers, just in a different position, and the odd ones have minus signs on them. No surprise there, right? Okay, so so all of this stuff is kind of related. All three of these formulas. Yeah, that's the main ones. There's a couple others on the sheet. I wrote down the cofactor expansion formula. That's kind of a lot of notation. You need to make sure you know how to find the determinant using cofactor expansion. Kind of already talked about that. But I think I'm going to leave the rest of that for you guys to just look at. You can look it up. Yeah, Curtis?
Just taking it back a little bit, with the simplification of the differential equations,
Yes.
a lot of time in the answers in the book, it like gets it all the way to y equals, even
Oh,
if you
right.
have to like exponentiate and take like inverse cosines and stuff.
Right. I will be very clear with you as to what form I expect your answer to be
Okay.
in. So if I write something like, you may leave your solution in implicit form. Implicit form means you don't have to solve it for y, you just need to have an expression that is in terms of y that you've obtained by solving the equation,
Right.
right?
Right, no.
If I say, please find an explicit solution means it needs to be in the form of y equals. If you were to do a problem and you did not go that full distance to getting an explicit solution, but you did everything else right and you had an implicit solution, you're still going to get the majority of the points, probably 85% of the points or more on that problem, but probably not full credit. If I ask for an explicit solution, you should solve it all the way for y. Usually I will ask for an explicit solution if I think it's reasonable that you guys should be able to do it without a whole lot of headache, right? If it's something that's really rough or it's using functions you've never seen before, I probably won't ask you to do it. But if it's things like exponentiating or moving absolute value bars off to another side or the stuff of that nature we've seen before. We've done it in some of our examples here. So I would likely expect you to be able to do that. And if that's what was involved, I would probably ask you for an explicit solution. I'll try to be very clear with my instructions as to what form I expect things to be in. But if there's any doubt while we're taking the test, you guys should feel free to ask me about that. Okay? Any other questions on kind of these formulas that we went over here? Okay, great. I'm going to take another pause break.